My name is Mena Malak, this is Hani, Kazemzadeh, Nelvin, Chery, and Lamy. And our factory advisor is Dr. Sabri Tosunoglu, and the sponsor is Mr. Norman Workman, who will be presenting the automatic self-folding machine. Our problem statement was to design and manufacture a machine that wraps and folds a sub-sandwich. The motivation was to design a wrapping machine to be used in sub-sandwich stores as Subway and Quiznos by House. The objective was to minimize waiting time and hand contact. The machine must meet all the government requirements and regulations. The machine must be safe, efficient, and cost-effective. So first we came up with 3 different designs. Actually, the first design was the 2014 team. The 2014, yeah. We didn't work on it because if we continued working on it, it was going to be so expensive. According to the reports, that part of the project cost $700. So we came up with the second design, which we built out of wood just to test the concept and see if it works or not. Our problem with the build, because the build was going over all the 3 shots, and then our final design is all the way at the end, which was actually easy to take apart, clean maintains, and it cost $468. The design consists of 3 shots, 4 shots. 3 of them are fixed, and 1 is attached to an arm that moves back and forward by a servo motor. The 2 bottom shafts, we attach the belt to the 2 bottom shafts using Velcro, and those are the ribbon shafts where the staple motor is attached to. So the process is the fix of the process. The first step is when the employees place the sub-sandwich on the belt, and the second one, the front shaft will rotate about 3 to 4 revolutions just to allow the sandwich to drop between the 2 shafts, and then the arm will move forward to cover the sandwich, and then both shafts will rotate in the same direction around the table to roll around the sandwich, and then the arm will come back up to bring the sandwich up for pickup.
For design and specification, we had to follow several standards and regulations. For the manufacturing, it's supposed to be food graded, as well as supposed to be stainless steel 316, and the convertible has to be food graded as well. The coefficient of correction for convertible was between 0.3 to 0.4. And we used different electronic microcontrollers and stepper motors, as well as temperature sensors. Whenever the machine heats up, the machine gonna stop by itself automatically. And for distance sensor, when the person places the sandwich on the machine, it does the job automatically. And we use Velcro to attach the belt to the shaft. We had several challenges during this design. First and foremost was the programming, since we didn't have vast knowledge of the programming. And other part was belt misalignment, which we will overcome by redesigning the shaft as is shown in the slide. Selecting the split in order to wrap the sandwich properly and perfectly. And the material selection for the belt was another challenge. We use a set of regulations and standards such as FDA, because the machine is going to be used in the sub-sandwich restaurants, and we got to follow those codes, and as well as American National Standards Institute. And because we want to market the machine like worldwide, we got to follow the international standard organization as well. For the bearing length, we use APA procedure, American Bearing Manufacturers Association. For global design integration, we use the components that could be easily found everywhere in order for the person who maintains the machine to easily change it. That's why we use SI and US units. And for the future work, if we manufacture this machine, we're going to develop a user's manual in 3 different languages, so it will be easily used in different countries. And we had several considerations during this project. Health and safety was the first and the most important one, since this machine is going to be used in the restaurant. Manufacturability is another consideration. It has to be like working, and it's supposed to be cheap as well. And the maintenance is supposed to be easy. Like it's really easy to change the belt or to clean up the machine since it's metal. And standard and regulation, which I already discussed on the other slide. And the size of the machine is important as well, since it's gonna be placed in a small counter, so it has to be size effective as well.
For a prototype cost report, we have for the shafts, the sensors, and the metal material in total, we spent a total of $468.82, and our machine list parts are there. For our prototype engineering labor, we have our estimated hourly wage, how much we would normally get paid to do that on that chart. And we have our manufacturing costs and component costs for you. For our bearing selection, we wanted our machine to at least run for at least 3 years without having breakdown failure problems. We wanted our bearing to last 3 years. It had to be food grade bearings at the bore diameter at least 3/8 of an inch. That's what our criteria for that. And we wanted flange mounted so we could mount it onto the machine easily. Also, we want the bearing to be covered so the grease inside doesn't leak out. And on the receive and run cycle, we wanted our machine, because the main purpose of our making this machine is so that we can cut wrapping time for sandwiches or like Subway or regular Subway sub-folding places. Normally they fold their sandwiches in 5 seconds. We want to beat that time with 4 seconds, and we calculated normally they on average make 500 sandwiches per day, and our machine would make the sandwiches and make daily 0.56 hours. Make 0.56. It would spend 0.56 hours a day to wrap a sandwich, and per year it would take 202.78 hours per year to wrap a sandwich, to run cycles to wrap a sandwich, which cuts the time by 18%.
So here we have the programming logic for the prototype, and in here the temperature sensor is not included in this logic. But we have the temperature sensor, the distance sensor, sorry, that checks for an object, and once it senses the sandwich, then the first motor rotates to loosen the belt, and then as you saw before with the steps, it goes under, and then after that happens, then the servo motor moves forward 26 degrees. It pulls onto the sandwich, and then you have both motors rotating clockwise the same direction. And after that process is done, then the servo motor moves the arm back, and then the sandwich comes up, and the programmer moves over and waits for another sandwich. Next. Here's the electronics diagram for the machine. We have a power supply that takes in 120 volts and gives out 12 volts DC with a 3 amps. And we have a 5-volt relay for the Arduino. And we also have, we're using 12 volts for our micro-step drivers for the motors. For simulations setup, we first, because we found the weights of the sandwiches online, but we wanted to test the weight of like a sandwich that's kind of over the standard size. And we weighed a sandwich we bought from Subway. Here's the setup for the simulations. We use stainless steel for the material. Here's the meshing condition. And here's the setup for the simulations on different components. Under the shaft, under loading, I have 1.31 pounds for the sandwich, and that gives us 129.94 maximum Van Mises stress on the shaft, with a really low deflection, the factor of safety of 46.17. And here we have the motor gives out a maximum torque of 26.3 pound-inch. So that's basically, we're assuming that the one end of the shaft is stuck, so that will be the maximum torque applied on the shaft. And with that, we have about like over 4,000 psi pressure, psi stress on the shaft, with 0.033 inch deflection factor of safety of 1.38. And here's the frame. For the frame, we can optimize to get the frame to get a lower factor of safety, but we would have a lot more deflection of the frame. So so here's the simulation results for the frame. Here's for the folding arm, the servo arm that's moving forward. For testing evaluation, so first, here's our first prototype that we made out of wood. We had a couple of issues with integrating the electrical components, the microcontroller. So we made some changes to the design to make it easier to integrate everything. With that, we took out the cutting, and as you see, the poster lists a lot of more tasks that we're supposed to do, but we found it to be most efficient to do this with the prototype. And here we have the sensor calibration. We calibrated the sensor so that it would only sense the sandwich at the spot where the sandwich is supposed to be. And here's our values at different distances from the sensor. And we have manual wrapping testing, and also the testing we actually calibrating all the components to wrap the sandwich. Here's our Gantt chart, and here's our final prototype design. Here's the setup of all the components in the machine. That's the rendered picture of the machine, and this is a video of the machine working. So the operator places the sandwich on the belt. The sensor senses the sandwich. It goes down. It starts to rotate the wrap, and for effect, you can see the sandwich wrapping inside the shaft, and that's how it's going to be folding the sandwich. And after it finished wrapping, the arm opens up and the sandwich comes up. And as of right now, we're doing more tests to make sure the sandwich, we get the right tightness of the paper on the sandwich. And we actually went to Subway, and we figured out, we found out that the paper is not that tight on the sandwich anyways at Subway. So here's our final prototype video. For future work, we plan on working with senior teams from electrical and computer engineering to better integrate the components into the machine, use more accurate sensors, better design the electrical components of the machine, and actually design our own PCB board with the microcontroller, with the chips, so that we don't use Arduino, because in mass production, $34 times a certain amount of different machines is a lot of money. So we want to do that. We also want to fully automate the sandwich making process, from choosing the topping to the wrapping, as well as adding the cutting and bagging to the machine, and also streamlining the prototype for mass production. Thank you. Any questions?
Pinch points. Do you have any plans on how to protect people from getting their hands into those belts?
First, we eliminated most of the pinch points, as you can see in our prototype, by covering most of the areas. So for now, it doesn't have as much pinch points as it once did in the.
I understand, but you've got moving drives and a belt.
Yes.
You have to make sure people can't get into it. That's a concern.
Okay.
But we have a plan to add sensors if it senses
A light rail or something like that.
and it stops the machine. And this button gonna stop the machine. Like,
See,
this is running, and you wanna stop it, and this is like.
That's too late.
So is your hands getting wrapped?
That's too late. That's too late.
Hey, extra hand sandwich.
Yeah. Okay. Another question is cleaning the machine. It would make sense to put a tray in the bottom of the machine that you have the ability to pull out, clean out all
I
of
just
the.
mentioned that right before we came here to Mr. Norman. We thought about it very late, and it was just we didn't have the time to add it.
Okay, and then last, I guess one more. When you finish your process, the sandwich is still down in the bed.
Mm-hmm.
It would have been nice if you by pulling the belt up flat, so the sandwich sits up on top of the bed.
all of that
That
is
would
with
save
the challenges that we have with the programming, because we're programming 2 stepper motors, and we found out stepper motors are a lot harder to program than we thought. And you have a motor that's we actually brought down the steps to like under 1 step per like the step per degree of the for the stepper motor, and we had to figure out a way to keep tweaking the program, still rapid. So we spend probably over 4 days just doing that. So
That's
it's-
reality.
So it's,
Actually, on the testing, if you look at the video, it comes up, but we couldn't get it in
You couldn't
the
get it to
final.
Final.
Yeah.
Maybe the widths need to be wider or something.
Probably, yes.
And then, of course, the last one. Other folks use $30 an hour. You use $35 an hour. Why are you $5 an hour better than they are?
the reason why is because we have to learn on the job. That we have to. That is
Because
It should
we
be
had to
less.
use the program, electrical engineering was
See, I'm saving you money here. But
We're like a lot of the components that we have to integrate into this are kind of above our expertise, and we have to learn extra. We have to gain more knowledge outside of our expertise to make the machine work. That's why it's a little bit more than.
Now, earlier you were talking about the wait time. You cut the wait time by what, 18%?
18%, yes.
Now, what is that in terms of hours, man hours?
Man hours,
Per month or per year?
amount per year. Normally, I have it on the slide, I just didn't say it.
202 hours a year.
Yeah,
How many?
202.
Two hours per
That's
year.
half-
It
that's-
was
that's
half
our
an hour per day.
More than
Yeah.
half an hour per day.
No,
0.55.
You would spend
But
500.
you look at this machine and you just see it's wrapping, you think it's useless. But in a future work, imagine like it's part of a bigger machine that does the sandwich automatically, fully automated machine. You have like moving arms to make the
Probably has
sandwich,
better
you choose your
consistency,
topping,
So,
and it will be part of that.
so 202 hours per year. In
Yeah.
terms of money, how much was that, roughly?
Let's say $12 an hour. You know,
Remember how much was it? 90?
$4,800.
oh, well,
So you're
that's
saving
sort of
that amount of money.
12
pays for itself and how much
Exactly.
time exactly.
that's really the key stage.
But
That's what it's,
anything being
it's
there
it's
is
an effort
better
that
not being
how quick
there.
does it pay for itself?
That's,
But the fact
that's
that
what
they,
they
Lloyd can have his
Plus
hands
cost
free
of
while
living.
the machine is wrapping the sandwich, he can be doing something else, chicken customer out.
Yeah,
You're on a
it's
political customer.
it just saves.
One of three does.
Every time is you can't get back. It's
But the good thing is you probably get
And the
consistency. Everything will be the
overall,
same all the
in
time.
terms of
Some are
how
not
many
wrapped
man
right
hours
now.
or say or
Making people with the big
say
little
the
hands.
future
Yeah.
work, when the next team works on this machine, they'll be doing less research and development and more testing. So they'll be able to gather all the data of how much an employee gets paid and actually go more in depth into measuring the time it takes one employee who's making a certain amount of money an hour to wrap the sandwich and how much time it saves. So they'll have more information on the how many man hours the machine saves.
So design consideration until you put sensors or whatever it is to protect the user. Something we see a lot in machines is you put two switches, for example, on opposite sides of the machine. So you don't have a chance of
Yeah,
turning
exactly.
it on with your hand and you both hands off.
Mm-hmm.
And for that it would just be a repositioning of your switch.
Any more questions?